Welcome to Homework Lib.
Here we're given the rotational constants for two different molecules. In this case, we're going to have aluminum and silver iodide. And for each of them, we're going to be given the rotational constants. So for aluminum iodide and for silver iodide, the value for B is equal to 3528.5533 megahertz in the first scenario, and on the second one, 1345.1103 megahertz. Let's remember a little bit on rotational spectroscopy that the energy for the rotational levels are going to be equal to J times J plus 1, a rotational constant B. And at the same time, the rotational constant is going to be equal to h bar squared divided by 2 times the moment of inertia within the rigid rotor approximation, which is going to be equal for a diatomic molecule, h bar squared divided by 2 times mu r squared, where the value for mu is equal to mass 1 mass 2 divided by mass 1 plus m2. So from here, in both cases, we're not going to know that the bond distance is going to be equal to h bar squared divided by 2 mu times b, and over here taking the square root for all of these values. So what we need to calculate for both of the molecules is going to be the value for mu, and the value for B is given already to us. So let's begin with the value for mu for aluminum iodide. This is going to be equal to the mass of the first one, which is aluminum, which corresponds to 26.98154. Remember that over here we can use it in grams per mole and then transform it into kilogram per molecule, employing Avogadro's number, or we can simply state it as atomic mass unit. Both of the approaches are correct and the equivalence is exactly the same value. And over here we're going to employ the mass of iodine, which is going to be 126.9 atomic mass units. 126.90 AMU. Just to put a value that is within the same amount of significant figures, this is 126.90447 atomic mass units. And over here, we're going to divide it by the mass. Add it up together. 154 atomic mass units plus 126.9447 AMU. Notice that the result over here is going to be in atomic mass units and is equal to, this is going to be equal to 22.250,743 atomic mass units. That, if we transform this into kilograms, remembering that one atomic mass unit is going to be equal to 1.6605402 times 10 to the minus 27 kilograms. This gives us 3.6948 477 times 10 to the minus 26 kilograms. Over here, we're taking as many decimal points as possible because it is going to be convenient when we want to do our calculations and find the difference in distance. And on the other hand, we're going to have the result for AgI, which I'm going to state just the final value. Remember that over here, this would be the mass of silver, which is 106.9051 atomic mass units, multiplied by the mass of iodine, which is 126.90447, divided by the sum of both of these values. Plus 126.9447. The final result for silver iodide in kilograms is going to be equal to 9.635.23.075 times 10 to the minus 26 kilograms. So now that we have both of these values, we can plug them in and find what would be the bond distance. Remember that our B constants need to be exchanged for, instead of being in megahertz, we need to put it in hertz directly, right? So let's do the example first for aluminum iodide, and then we're going to do the other result. The value for H bar is going to be equal to 1.05457 times 10 to the minus 34 joules second. All of this is going to be squared divided by 2 times the value for mu for aluminum iodide, which is 3.69, 48, 32, 477 times 10 to the minus 26 kilograms. So over here, we need to plug in the value for B in the correct units. So as you can see, over here, B needs to have units of energy. But the values that we're given here, let's call these B primes, are in units of frequency. So how do we transform from one to another? Well, energy is equal to H times frequency. So we need to multiply both of these values by our constant H. So let's put it in here, aluminum iodide in this case. So B for aluminum iodide would be equal to the value for H, Planck's constant, which corresponds to 6.626070 times 10 to the minus 34 joules second, multiplied by the value in megahertz. Recall that the value in megahertz corresponds to 10 to the 6 hertz, right? So in this case, for aluminum iodide, the value that is given to us is 3,528.5533 megahertz, which is times 10 to the 6 hertz, which is seconds to the minus 1. So this value is equal to 2.338044 times 10 to the minus 24 joules. So replacing that value in our equation, the result for R is going to be equal to 2.537 1026 times 10 to the minus 10 meters, which is the same as saying 2.5331. Let's round it up as 3103 angstroms. Remember that 1 angstrom is equal to times 10 to the minus 10 meters. So now we're going to repeat the procedure, but now with the silver iodide. So instead of replacing all of the values, I'm just going to do the calculation for the actual rotational constant for AgI, which is Planck's constant, 0.70 times 10 to the minus 34 joules second, multiplied by my value in megahertz, which is 1345.1103 megahertz, which is times 10 to the 6 hertz, second to the minus 1. So the value for B of AgI is equal to 8.91279.501 times 10 to the minus 25 joules. And upon calculation, the distance of AgI, which I'm just going to follow the same procedure dictated by this formula and replacing the values corresponding to the reduced mass of silver iodide, gives us 2.544.62 1, 2, 3, 4, 5, 6, 4, 5, 62, 1 times 10 to the minus 10 meters, which is the same as 2.544 angstroms. So this is going to be the bond distance for both of the compounds. And this is how we differentiate one from the other. As you can see, the difference is in the order of times 10 to the minus 12 meters. So a very small difference. So with that, it would be all. Just as a recap, remember that the rotational constant is related to energy. We have this value for the rotational constants. In this case, the rotational constants that were given to us are in terms of frequency, so we need to convert them into energies, as we did here and here. And additionally to that, the only extra step, since we're dealing with a diatomic molecule, the moment of inertia is mu times r squared, and we need to calculate mu precisely enough to get the correct result. So with this, taking all of the significant figures and making this as accurate as possible, these are the final results. So with that, it would be all. Thank you very much and have a good one.